All right, so I think I'm recording. Let's take a look at these three equations. They want us to solve these. And although they're not quadratic equations, they are what we say quadratic in form. Um, if you'll notice that the first term has a degree of 4, and the second term has a degree that's half of that. And that's true for all three of these problems. So there is a technique that you will see in higher level math courses in calculus that is called a U substitution. And truly, all it is to make this look um, in a form that you're familiar with. So we're going to start with that, always with that middle term there, and we're going to let x squared be u. And I'm also going to square each side of this equation. And remember that when you have a base, when you have a power raised to a power, by our properties of exponents, you multiply the exponents. So if I square both sides of this, then I have 2 times 2, which is 4, and u squared. So everywhere, now I'm going to do a substitution that everywhere I see an x to the fourth, I'm going to replace it with u squared. And everywhere I see an x squared, I'm going to replace it with u. So the first term is x to the fourth, but I'm now going to write that as u squared. And then it's minus 9x squared, but I'm going to replace x squared with u. So now you can see that this is a quadratic equation, and we can solve it like we do any quadratic. We can hopefully factor it. If it can't be factored, we can always use the quadratic formula or complete the square. So here I believe this can be factored. So let's go ahead and well, I don't necessarily have to do the x method because with the leading coefficient of 1, it's normally pretty easy to factor if we can. So two numbers that multiply together to give me a negative 10, but add together to give me a negative 9 are negative 10 and positive 1. So this is very easy to solve. We know that u is equal to 10 or that u is equal to negative 1. We can see that by inspection. But now we have to remember that the original problem did not ask us to solve this for u, it asked us to solve it for x. So we come back up here and we say, well, we're going to substitute back to our original variable, which was x. So everywhere I see a u, I know that's equivalent to x squared. So I have that x squared is equal to 10, and over here I have that x squared is equal to negative 1. Now that should give off warning signals that within the set of real numbers, that's impossible. How can you have a number times itself ever be negative within the set of real numbers? We can't. So this provides no solution right here. But the other side does. If we take the square root of each side, then of course we have to introduce a plus or minus symbol whenever you take the square root of a variable. And our final answer, our solution set, is plus or minus the square root of 10. All right, now let's tackle this number 2, and we'll do it in the same way. We see this x squared, and we're going to let x squared be u. And we're going to let x to the fourth power, if we square both sides of this, be u squared. So that means that this equation that is not quadratic, through this change of variable, provides a new equation that has the same solution set that is quadratic. So instead of 3 times x to the fourth, we have 3 times u squared, minus 22 times x squared, which is really now minus 22 times u. Now this one, I don't know if it can be factored or not, but I'm going to try. And since the leading coefficient is different than 1, I'm going to use the x method to do it. At the bottom of the x is our middle term, and at the top of the x is the first term times the last term. And so now the trial and error portion begins. I need two numbers that when multiplied together give me the top number, but yet when added give me the bottom number. And I think, excuse me, a negative 10 times a negative 12 does the trick, because the negative times the negative is positive, and when I add these together, I get the bottom of my x. So, since my leading coefficient was different than 1, I'm going to come over here in the form of a table, and along one diagonal, I return to my equation and write the first term and the last term. And this, this middle term now, negative 22u, has been split up into negative 10u and negative 12u. So now I can factor this. Now whenever I have a diagonal that's negative, I'm going to factor out negative numbers out here, a negative 10 and a negative 4, because negative 10 times a negative 4 is positive 40. If I look here, I have 3u, and if I look here, I just have u. And let's check and see if I've done this correctly. 3u times 1u is 3u squared. 3u times a negative 4 is negative 12u. Negative 10 times 1u is negative 10u. And we already saw that negative 10 times a negative 4 is positive 40. So this allows us to factor this trinomial into a product of two binomials. And it's easy now by inspection to solve this. When it was a trinomial, I couldn't look at it and just tell you by looking at it that the solutions to that equation were 4 and 10 over 3. But now in factored form, I can definitely tell you that. See, I can solve for this u in 2 steps, to add 10 and divide by 3. And here it's just a single step, just 4 minus 4 gives us 0. But remember, just like last time, I need to replace this u back to x squared, because really what I'm trying to solve for is I'm trying to solve for x. We just made that change of variable so that we could put it in a form that was recognizable, a quadratic form. Because of all the equations and things that we've done in high school math, in every single class you have worked with quadratic equations. All right. So now, if I replace u with x squared, I have x squared is equal to 10 over 3, and I have that x squared is equal to 4. So over here, I have plus or minus the square root of this fraction, and over here, I have plus or minus 2. Now, we have a little bit of a problem that we haven't seen in previous problems, and that's with our radical there, that we're not allowed to have a fraction underneath a radical. We're not allowed to have a radical in a denominator. And remember that from our properties of radicals, that the square root of a over b is the square root of a over the square root of b. And that's not allowed. It's against the rules to have a radical in the denominator. Now, I think those rules myself are a little outdated, but I go with the grain. I don't go against the current on that. All right, so I have plus or minus 10 times 3 is 30. And the 3 times 3 is the square root of 9, but the square root of 9 is 3, and now I don't have a radical in my denominator. They refer to that as rationalizing the denominator. All right, so I have my 4 solutions. You know, as I think about it, it probably would have been a smarter answer to not say no solution, but like I had done in previous videos, and to say no real solution. Because there is a solution to that equation, it's just that it involves complex numbers. So here's a better, I want to modify that, my answer to number 1. And I'm not going to redo the video to just, I hope you understand, just to make that uh, change. All right, I'm going to move my properties right here out of my way. Maybe I should just go ahead and cut them completely out of the way. All right, now I think I have enough room over here to do this. All right. So again, I'm going to do what they refer to as a U substitution because I see this as quadratic in form. The exponent on the middle term is half of that that's the exponent on the first term. So I'm going to let this x squared, this middle term, I'm going to replace it with u. And when I square both sides of this equation, I get x to the fourth is u squared. So I'm going to do a substitution. Everywhere I see x to the fourth, I replace it with u squared. And everywhere I see x squared, I'm going to replace it with u. And now I'm familiar with this type of a problem. This is a quadratic equation, and I can factor this, and I can factor this pretty easily because the leading coefficient there is 1. So I can see that this is going to factor to u plus 6 times u plus 1, because 6 times 1 is 6, but 6 plus 1 is 7. And this gives me solutions of negative 6 and negative 1 for u. But when I go to replace u with x squared, I see that I have no real solution for both of these. So my final answer, the solution set for this fourth degree is all complex numbers. It's all going to be, remember, complex numbers are of the form a plus bi, where I is the imaginary unit. So here's my final answer for these three. Ask any questions as needed. Let me know if I've made some type of silly error on these videos so I can edit them and help other people. But you'll have to get used to this through practice. This is not something that you have seen before, but if you're going to take future math classes, I guarantee you will see it. So you want to try to get used to it now, because there'll be other things that'll be harder in calculus that you'll want to spend more time studying the harder things rather than this U substitution. Talk to you later. Bye.